about, we're going to talk about the difference between rotational and translational motion, to introduce rotation, because we've been discussing translational motion all year long. You are going to get some equations today to copy down, and we're going to look at some graphs as well. I do have a list up here of kind of upcoming deadlines. The Unit 6 Playlist 1, which we're starting today, is due on the 28th. Your roller coaster lab write-up is due on the 23rd, and so is your bump assignment. So if you haven't been paying attention to that, or those upcoming dates, that is in 2 days, so on Friday. And then retests, I did have some people ask about retests for Unit 5. Obviously, we also have corrections, FRQ corrections, but those, the deadline for completing your retest and turning in any corrections is on March 4th. Okay, so you do have some time still to work on those things. During class, if we have time, you can work on corrections, but otherwise in tutorials after school. All right, so translational versus rotational motion. All year long, we have been talking about translational motion. When we've discussed, a box sliding across the floor or down a ramp or whatever random scenario I've given you, it's always been a discussion of translational motion where we assume that all parts of the object undergo the same motion and it maintains the same orientation, and we're not taking into account any rotation. We're assuming there is no rotation. Okay, so this is what we've been talking about all year. Today we're going to, and in this unit, we're going to talk about rotational motion, which is when all parts of the object are going to move in a circle around some axis of rotation. Okay, so now we're going to be talking about things that are spinning or possibly rolling, in which case we'll be dealing with both translational and rotational motion. Okay, but when we have rotation, we're going to be looking at things that are rotating about an axis of rotation. So translational motion, you'd have something like this where the object, moves for 5 meters or however long, and so it's just, again, translating across the screen, and there is no rotation. All parts of it are moving at the same rates. It's not rotating about, whereas this one has motion as well, but it is just rotating. Of course, if you were to combine these two motions, you would get rolling. An object rolling across the ground would have both translational and rotational motion. Okay, objects undergoing translational motion and or rotational motion, because you can have both at the same time, or just one or just the other, both experience a change in position. Okay, so when we talk about our objects undergoing translational motion, we talk about how far they move across that surface. But when we can talk about objects that have a change in position, or we can talk about their velocity or their rate of change of velocity about their axis as well, which is what we're going to be looking at when we look at rotational motion. And so we can talk about changes in position or changes in velocity or rates of acceleration whenever we're discussing things that are rotating as well. Okay, so it doesn't just have to be translational. We're going to look at it rotationally. So this is what we've seen this year. This stuff should look familiar. When we've talked about translational motion, we've talked about the position of whatever the object is in terms of x. That's the variable that we see in our equation. But we say, we can determine an initial position, a final position. We called that, x naught and x. But we can talk about its position, and we measure that in meters. When we discussed velocity, it's represented by the variable v. That's how it shows up in your equations, and it was measured in units of meters per second. And when we talked about acceleration for our objects undergoing translational motion, we used the variable a, and we measured our accelerations in meters per second squared or meters per second per second. Okay, so all of this looks familiar. It's the same type of idea when we look at something that's undergoing rotation, except when we look at an object that is rotating and we want to talk about its change in position, we're going to be talking about its change in its angle, okay, as for that point on the object as it's rotating about this axis. And so if we have a change in an angle, we're going to talk about our positions in terms of theta, okay, and those angles in terms of radians. And so that will be your unit, will be radians. When we talk about angular velocity, we'll be talking about the rate of change in position, just like we did with translational velocity. It was the rate of change in position there, the change in x, whereas this is the change in theta. And we use the variable omega for angular velocity. These are all Greek letters, by the way. But we have theta for angular position, omega for angular velocity, and the units for omega will be radians per second. And then for angular acceleration, if we have a rate of change in our angular velocity, if it starts rotating faster, then we could calculate an angular acceleration, and that will be alpha is our variable for angular acceleration. It will be in terms of units of radians per second squared or radians per second. Okay, so again, we've been using our calculators all year long, and I've been telling you over and over again to make sure you're in degree mode. Well, guess what? Now we need to be in radians. Because as you can see by the units up here, for rotation, we are going to be measuring those angular positions in radians, and therefore the rate of change will be in radians per second. And if we have changes in the velocity, again, same thing. Okay, so just keep that in mind whenever you are doing any calculations. You won't want it in degrees, you will want it in radians. So again, this is kind of summarizing what we just looked at. So with our translational motion, these were our variables. With rotation, same variables. And we can calculate average velocity, and the equation is basically the same thing. Average velocity is going to be your change in position over time. That could be a change in translational position over time, in which case you get that equation that should look familiar on the left. Or it could be a change in rotational position over time, in which case you get the equation on the right. And so they are analogous to one another, and you're going to see this over and over again. There are basically rotational equivalents to our translational equations, which does make it a little bit easier because it makes the math feel a little bit more familiar, because it's basically the same equation. It's just now we're talking about it in terms of rotating about an axis. So our formula for average rotational velocity is, again, average omega is equal to change in theta over time. All right, so we can relate the two types of motion to each other. So again, whenever we're talking about rotation, the axis of rotation is the center of this circle. So if I have an object that is rotating around a point, the axis of rotation in this example, I'm putting it right here, and it's rotating, out here along this circle that I've drawn. Okay, the angular positions are going to be in terms of pi, which is a radian. And so at 0 degrees, we're going to say that's 0 radians. If you have rotation to 90 degrees, that's going to be pi over 2. Does this look familiar, you guys? If it rotates 180 degrees, that's going to be pi. I know some of you are like, oh, this is why I had to do this in my math class. 270 degrees is going to be 3 pi over 2. And then all the way back 360 degrees is 2 pi. Unit circle. Yay!
Will we ever need anything between it?
Sorry? Yeah.
Other ones? Okay.
Okay, so again, we're going to do our positions, so you might want to draw this on your paper so you can refer back to it. But your positions, again, in terms of pi, which are your radians, which you can see on my unit circle here. Now, when we're talking about an object that's rotating, okay, we can go from rotational to translational motion. We can look at a linear distance that is covered as well, and to do that, we'll have to look at something like this, where we see this arc length. That will be the linear distance that the object has traveled as it is rotating about the axis. To get from radians, from our rotational motion to linear motion, you just use that arc length, or this equation here, and you say x, that's the length of that arc that we drew up here in green, is equal to, and again, you should remember this from math, hopefully, but the radius times theta will give you your arc length. Okay, and so you can go from rotational motion to translational motion and figure out like a linear distance that is being traveled with this equation. And you're going to see that same relationship. It's going to be a pattern. I told you it's going to look familiar as we go through them, because that same rule holds true for everything else. You can multiply by radius, which is what you're going to see here. If you want to look at position, you can take your theta, your angular position, and multiply it by radius, and now you have your translational position. You can multiply your angular velocity by the radius, and you will get your translational velocity. You can multiply your rotational acceleration alpha times radius, and you will get your translational acceleration A. And so you can use this rule for everything, pretty much. If you multiply by that radius, and that's what it says, the same pattern will relate all equations from rotational to translational, just multiply by the radius. Okay, and so if you're trying to answer, depending on what question you're trying to answer, you might need to do this. You might need to just take that and multiply by the radius to get from that translational velocity, for example, from a rotational velocity rather to a translational velocity. So V equals R omega, for example. Again, I would just copy the equations down and whatever you need to remember what all these variables stand for. Okay, so again, I said they're all related. We can also, because we've looked at things moving in circles before, we did a whole unit on uniform circular motion. But in uniform circular motion, again, we were dealing with things where we were talking about a linear velocity. And you can relate it to rotational motion as well. Okay, and so that's what I have here is my centripetal acceleration was equal to v squared over r. That's the equation that we learned. But we just learned that we can relate that to our rotational motion by just multiplying by r. And so I have r times omega. That's my angular velocity times my radius. If I substitute that in, okay, I get this equation. And it simplifies to this. And so I can say that my centripetal acceleration is equal to my radius times my angular velocity squared. Okay, so again, depending on what you're trying to answer, do keep in mind though that centripetal acceleration is still that inward acceleration toward the center of the circle. When we talk about that, that is not the same thing as alpha. Okay, our rotational acceleration is the rate of change in the angle about that axis of rotation. So they're not the same thing, but again, you can relate the translational motion to the rotational motion. All right, so all points on a rotating body have the same angular velocity and cover the same change in angle. So if I look at like any of these points that I've labeled on either of these, okay, they all have the same change in angle about this axis of rotation. They don't have the same linear position change, but they do have the same angular position change. Okay, and so whenever you look at this, we can use this equation, which we've already looked at, to say that our angular velocity is equal to our change in theta, so again the change in the angle here, divided by time. Again, we have different linear positions here, and our linear displacements are different, and we talked about that in our circular motion unit, but when we're talking about angular, you need to keep the two separate in your head. You can relate them, but they're not the same thing. Okay, so those are the different linear distances covered, but the angle is the same for all of those. So this is a quick little video clip of a marching band. The resolution's terrible. You might be better off watching it on your own screen. But when you look at this, you're going to see when I play it in a second that the band members that are near the axis of rotation have this small linear motion, but they travel with the same angular speed. They do have the same change in angle per second as those that are farther away, but they don't have to move very far in comparison when we're looking at that linear or translational motion. I'm going to turn the music off, y'all. You can't hear it anyway from my computer screen. But again, like the guy that's standing here in the middle doesn't have to do much of anything, but the angle is changing. Obviously, the people standing farther out on the outside have to cover a greater linear distance per second, but their change in angle is the same for the entire line of people there. Go past that.
Go back for the dudes on the
Okay, we can also discuss angular velocity in terms of frequency. Okay, when we talk about frequency, we're looking at the number of rotations per unit of time. So it might be the number of rotations per second, depending on the object, if it rotates quickly. If it's slower, it might be a longer unit. And again, we can relate frequency to angular velocity using 2 pi, because we're talking again about the rotations about the circle. And so if you wanted to know the frequency of an object, you could set it equal to that angular velocity divided by 2 pi. And when we talk about the velocity, angular velocities of these objects, or whenever we need to add a direction to it, our only directions are going to be clockwise and counterclockwise. And so you can see down there that we're going to abbreviate those to save us from, those are long words, to save us from having to write the whole thing out. If you're talking about a velocity that is, an angular velocity that is clockwise, you can use CW, counterclockwise, CCW, again down here at the bottom. And you'll see the same thing in your problem set, task options for this unit. All right, so when we talk about acceleration, we talked about it with translational motion already. When we had an object that speeds up, slows down, or changes direction, we said that that object was undergoing translational acceleration. When we talk about angular acceleration, so for objects that are undergoing rotation, we just focus on speeding up and slowing down. Okay, and so you'll have objects that have a rate of change in angle of their rotation that is changing. Okay, and so if you have that a changing angular velocity, then of course you will have angular acceleration of your object, whatever it is, causing it to speed up and rotate more quickly, or slow down and rotate more slowly. So if we have something speeding up, it means that the angular acceleration is in the same direction as the object's motion. So if the object is rotating clockwise and the angular acceleration is also clockwise, then that object is going to speed up. Okay, so again, if the angular acceleration is in the same direction as the object's motion, you'll speed up. That means they're either both clockwise or they're both counterclockwise. On the other hand, if your angular acceleration is in the opposite direction as the object's motion, then you're going to have something that is slowing down rotationally. So if you have something, for example, that's rotating in a clockwise direction, but is experiencing angular acceleration in a counterclockwise direction, then that object will slow down, eventually coming to a stop, okay, potentially changing direction after that and rotating the other way. But again, if they're opposite, you're going to slow down. If they're in the same direction, you're going to speed up. Same rules as before. We had the same thing that we analyzed with our translational motion as well. So here are the equations that should look familiar from your AP Physics 1 formula chart for our translational motion. Those are our kinematic equations. And here are the rotational equivalents, and they look exactly the same. The variable that we had, velocity, translationally this v, the angular velocity is omega, and if you look, these equations look pretty much the same. Now I have angular velocity equals initial angular velocity plus angular acceleration times time. Okay, so it's the same thing that we have over here. They're analogous to one another. That's what makes it easier. When you look at your formula chart, you're not going to see these equations on it for the rotation stuff. You just need to know that you can take these translational equations and get these rotational equivalents from them. Okay, so those are our kinematic equations for rotational motion as well. You may want to copy those down so that you have them to refer back to. Actually, I take that back. They are on there. They're on there. They printed them on there too. Okay, so I was just checking. But we do have at least the first two. I'm trying to see. I don't know if this third one's on here. The third one is not on here, but the first two are. But again, you can see this one. This is on there, and you can get this equivalent. All right, so when we talk about graphically looking at translational motion, Okay, we had maybe a graph that looked like this, where we had an object that was experiencing acceleration. There's a change in the slope of this line, and so this object was experiencing acceleration for its translational motion because the slope started out basically at 0 and then it gets steeper and steeper and steeper. Okay, when we graphed this and took the data to our VT graph to show the same thing, okay, or actually this isn't the same graph, but on a XT graph, the slope of the object, or the slope of the line, is your velocity. So a changing slope means, of course, you have a changing velocity. These are not showing the same motion, but again, we're just going to go over the rules. When we looked at VT graphs for translational motion, we found that the slope of this line was equal to our acceleration, and that the area under the line, or between our data points and our x-axis, so like the area of this triangle and then this triangle over here, would give us our displacement. When we looked at our AT graphs, again, we found that the area under the line or curve of our graph was equal to our change in velocity. Okay, so we've seen all of these graphs before for our translational motion. Again, rotationally, same thing. Okay, if you have a graph for rotational motion that has this same shape, the slope of that is going to tell us our angular velocity this time. And in this case, because my angular velocity is changing, I would be experiencing angular acceleration. Again, if I were to look at an angular velocity versus time graph, an omega t graph, same idea. The slope of this is still going to give me my acceleration, except this time it's alpha because it's my angular acceleration. The area under this curve, or line in this case, is going to give me the change in my position, except this time it's my angular position, so it's delta theta. Okay, but it's the same rules we saw up here. And again, when we get to our acceleration time graph, or rather alpha time graph for our angular acceleration, same thing. The area under this is equal to our change in angular velocity. So it's not, it is new, but it's not new. Like, there are parts of it that are, but a lot of this is going to be analogous to the stuff you've already done with translational motion earlier in the year. All right, guys, so for the rest of the class period today, you can work on playlist 1 for Unit 6, rotation, or your roller coaster data sheet and write-up are due on the 23rd. If you have not turned those in yet, that might be a good thing to look at. Your bump assignment, if you're planning to do it, which I would strongly recommend, also due on the 23rd. And I'm going to hand an inertia lab to you in just a moment, because tomorrow you're going to be doing a lab, and I'm going to ask you to do the knowledge probe before tomorrow's lab. There's only 2 questions on it, but I'm going to ask you to do that. As a reminder, Unit 5 test corrections are due by March 4th, and the retest deadline is also March 4th. If you guys have any questions as you're working on any of these things, please let me know.